Vertical stability of the atmosphere refers to the tendency of air in the atmosphere either to remain in its original position or to move vertically when it is disturbed. In simple terms, it describes whether air parcels will rise, sink, or stay at the same level after being pushed upward or downward. This concept is very important in meteorology because it affects cloud formation, rainfall, thunderstorms, fog, and air pollution dispersion. To understand vertical stability, meteorologists often imagine a small parcel of air that is lifted upward from its original position. As this parcel rises, the surrounding atmospheric pressure decreases, causing the parcel to expand and cool. The rate at which the air parcel cools is known as the adiabatic lapse rate. If the parcel is dry, it cools at about 9.8 degrees Celsius per kilometer, which is called the dry adiabatic lapse rate. If the parcel is saturated with moisture, condensation occurs, releasing latent heat, and the cooling rate becomes slower, usually about 5 to 6 degrees Celsius per kilometer, which is called the moist adiabatic lapse rate. At the same time, the temperature of the surrounding atmosphere also decreases with altitude, and this decrease is called the environmental lapse rate. The comparison between the environmental lapse rate and the adiabatic lapse rate determines whether the atmosphere is stable, unstable, or conditionally unstable. If the environmental lapse rate is smaller than the adiabatic lapse rate, the atmosphere is considered stable. In this situation, when an air parcel rises, it becomes cooler and denser than the surrounding air, and therefore sinks back to its original position. Stable conditions suppress vertical motion, which means clouds and storms are less likely to develop. Instead, the atmosphere may produce stratiform clouds, haze, or fog. Stable atmospheres also trap pollutants near the surface, leading to poor air quality in urban areas. Temperature inversions are a common example of strong atmospheric stability. In an inversion, temperature increases with height instead of decreasing, preventing air from rising and mixing. On the other hand, if the environmental lapse rate is greater than the dry adiabatic lapse rate, the atmosphere is unstable. In an unstable atmosphere, when an air parcel is lifted slightly, it becomes warmer and less dense than the surrounding air and continues to rise on its own. This rising motion can lead to the development of strong vertical currents, cumulonimbus clouds, heavy rainfall, lightning, and thunderstorms. Unstable conditions are often associated with intense weather events because rising air cools and condenses, forming large clouds and releasing latent heat that further strengthens the upward motion. This process plays a key role in the formation of severe storms and convection systems. There is also a situation known as conditional instability, which occurs when the environmental lapse rate lies between the moist and dry adiabatic lapse rates. In this case, unsaturated air parcels are stable, but once they become saturated and start condensing moisture, they become unstable and continue rising. Conditional instability is very common in the atmosphere and is responsible for many types of cloud formation and rainfall processes. For example, warm, moist air near the surface may initially be stable, but if it is lifted by mountains, fronts, or surface heating, it can become saturated and form towering clouds and precipitation. Vertical stability is influenced by several factors, including solar heating, surface temperature differences, moisture content, and large-scale atmospheric circulation. During daytime, strong solar heating warms the Earth's surface and the air close to it, making the lower atmosphere less dense and more likely to rise. This increases atmospheric instability and often leads to convective clouds in the afternoon. At night, the surface cools rapidly, making the air near the ground cooler and denser than the air above, which creates stable conditions. Topography also plays a role. Mountains can force air to rise, sometimes triggering instability and precipitation. Similarly, weather fronts, boundaries between different air masses, can lift warm air upward, causing cloud development and storms in unstable atmospheric conditions. Understanding vertical stability is essential for weather forecasting, aviation safety, and environmental studies. Pilots need to know whether the atmosphere is stable or unstable because unstable air can produce turbulence, which affects aircraft operations. Meteorologists analyze vertical stability using weather balloons that measure temperature, humidity, and pressure at different heights in the atmosphere. These measurements help scientists predict storm development, rainfall patterns, and the dispersion of pollutants. Vertical stability also affects agriculture because it influences rainfall distribution and the likelihood of frost formation. In summary, vertical stability of the atmosphere describes how air behaves when it moves vertically and is determined mainly by the relationship between the environmental lapse rate and the adiabatic lapse rates. Stable atmospheres resist vertical motion and produce calm, layered weather conditions, while unstable atmospheres encourage rising air, leading to clouds, storms, and dynamic weather events. Understanding this concept helps scientists explain many atmospheric processes and improves our ability to forecast and prepare for different types of weather.